So now we are moving to the final block of this event. We are going to talk about causal inference, basically, and LLMs. And in particular, we'll start on discussing the potential for automation or not. And we have the chance to have Nick Huntington-Klein, who is Associate Professor of Economics at Seattle University, and he's author of the book, The Effect. You can access also a version online of this book. And probably you know also Nick, because you've seen his very good educational YouTube videos about causal inference.
Let's go ahead and get started anyway here. So what we're looking at here is a pretty obvious question to anybody who's working in causal inference and has any awareness of all the developments that we've had recently over the past few years in AI and large language models. And the question that I'm looking at here today is specifically, do large language models act as repositories of causal knowledge is what we're looking at. And the reason why we might be interested in this is because we might want to know, well, to what extent can we really automate the causal inference process or not be able to do it, right? So the goal that we have is we want to do causal inference in observational data. That's what pretty much everything that you're seeing here today is about, more or less. We can't run an experiment, but we want to know the effect of one thing on another. And to do this, we need to have some sort of identification method, meaning we need to have some idea of how do we look in the observational data, which typically does not have a good sort of randomization procedure in it, and know what it is that we need to control for, or what source of sort of random-like variation do we need to pull out in order to isolate just the causal effect that we are trying to get, right? That's what we want to do. And a lot of the time what this means is picking an appropriate set of control variables, right? There are things that confound the relationship between the treatment and the outcome that make it so that we cannot tell the effect that we are interested in, right? If you want to know the effect of, going to the hospital on being sick, and you just look at the correlation, you might find that actually going to the hospital is correlated with being very sick. But the hospital isn't the one that made you sick. You went to the hospital because you were sick in the first place, right? So what are the things that we need to control for? Things like being sick already in order to isolate the causal effect that we're interested in. Now, doing this typically in an applied setting requires you to know a lot about your setting, right? You need to know a lot about the real world in order to know what's called the data generating process, so that you can know what are the things that are related to your treatment and outcome that actually constitute confounders that you need to control for. So here's the question: could a large language model do it instead? Can a large language model look at a relationship between a treated and an outcome, or a treatment and an outcome variable, and a potential confounder, and determine whether or not that variable belongs as a confounder, is a variable that we should control for? Basically, can it sort properly into confounders and non-confounders? So the question is, does this work yet? And the answer is no, not really, at least not yet. We'll go into exactly what we mean here. So we're looking particularly at one kind of way in which a large language model might be able to help automate this process of picking control variables and confounders. One way, which a lot of people have taken, is a reasoning approach, right? You could imagine that a large language model would be able to develop some sort of model of the world that is complex enough and complete enough to be able to say how things actually fit together, to be able to recognize that when it looks in its training data and finds that the words being in the hospital and sick are often appearing together, that it's not because the hospital made them sick, it's because of some confounder that needs to be accounted for, right? And so you could, in that context, ask a large language model whether something should be a confounder, and it might be able to figure it out, right? The other way that we can think of large language models as being able to do this is as a form of retrieval or recall, right? Large language models have ingested a huge amount of data, and they have the associations between different words. And also a lot of the data that they have might include people discussing causal relationships, right? You might have people saying something like, oh, you can't just look at the correlation between being in the hospital and being sick. You need to control for whether they were sick before, right? Somebody might just literally say that in the training data or something similar to it. And then it might be able to bring that information back, report it to the user, and therefore that's how you know that that should be a thing that you need to control for. So this doesn't actually require any sort of real understanding for large language models to be able to do this. It just has to be able to look at other kinds of discussions people have had about causality before and be able to bring that up. So a lot of the prior work on using large language models for automation focuses on the reasoning approach. We're going to try to look at retrieval, right? Can it bring back information from its training database, basically? And this makes sense. This fits better with how large language models are built than a reasoning approach might. Because here's an example, right? A good example of a confounder when studying the effects of hormone replacement therapy on cardiovascular health is what? Finish this sentence, right? And large language models are very good at completing sentences. And in this case, this is a sentence that more or less has appeared in its training data. There are multiple papers looking at the relationship between hormone replacement therapy and cardiovascular health and mentioning that socioeconomic status is a confounder in that setting. And so if you ask this question of GPT-4o, for example, it will tell you socioeconomic status. It's just bringing back a discussion that was already had in its training data. So here's the question, if expert opinion is in the training data and we need an expert to be able to help us sort confounders from non-confounders, maybe the large language models will be able to just tell us what the experts say and therefore accurately sort the confounders from the non-confounders. So we are going to use as a setting to test this something called the Coronary Drug Project. This was a large randomized drug trial from 1965 to 1985 looking at men who'd had a heart attack. They had a treatment arm where you got the pill that they were testing. They also had a placebo arm where you did not actually get anything, right? However, what they found is that in the placebo arm, where people did not get any actual treatment, they just got a sugar pill, people who took the sugar pill had much, much better outcomes than people who didn't, right? Now, this is not particularly evidence of a very strong placebo effect. Really, this is evidence of adherence, right? It was the people who chose to actually take the pill that they were assigned tended to also be doing other good things for their health, and therefore they did better as a result, right? So there's confounding here in the placebo arm. In 1980, when they first found this problem and analyzed it, they thought it was intractable. They could not solve the problem. There was a 13.1% gap in mortality between people who took the sugar pill and people who didn't. When they controlled for the things they had available at the time, it only shrank to 9.4% of a gap. They thought you can't really control for this. This study is unsalvageable. There have been a number of other studies on this project since then, improving the selection of confounders, and doing so has shrunk the problem a whole lot down to 2.5% to where they think that they can actually solve this problem, or rather the experts can solve this problem by picking out the appropriate confounders. So this is a case where the training model, the large language models have access to this training data that discusses very explicitly what is or is not a confounder in this particular setting. So this is a good test of this particular retrieval mechanism because we have a ground truth. So when the large language model tells us that something is a confounder or not, we don't just look at it and say, oh, that sounds right. We can actually check it against what the experts have previously said, because that's what we want. We want to sort of be able to say, can a large language model just do what an expert used to be able to do? We have 3 papers that did this. We have the CDPRG paper from 1980. This was the original set of confounders that found that they could not actually solve the problem. And there are 2 follow-up papers, one by Murray and Hernan in 2016 that did a reanalysis, and then there's another one from Debertine in 2024 that did a further expert causal diagram. So this is in the training data. We know that for sure because it's a very famous study. It's very heavily discussed. There's a lot of papers about the Coronary Drug Project and its placebo arm confounding. We know this because if we ask the large language models about the Coronary Drug Project in particular, without even prompting, they will come back and say, hey, did you know there's confounding in the placebo arm? Right? We don't even say that and it knows it. So somewhere in the training data is information about this study. So the expert opinion is in the training data as well. If they can retrieve expert opinion about causal links, it should be able to do so in this context. So we have 172 potential variables that we want to sort into confounders and not confounders. And those variables get set into 5 different sort of categories. The first 3 are ones that the experts say are confounders and should be controlled for using the 3 different studies that looked at this problem, right? The original 1980 paper, the ones that were added as confounders in 2016 that really narrowed that confounding gap from 9.4 to 2.5%, and then further ones that were added in 2024. We also, and this is important too, we have confounders that are not confounders. We have potential confounders that the large language model should be able to say are not confounders. These are ones that were considered but were rejected. These are the trimmed variables that were removed by expert opinion. And we also have the non-confounders. These are pretty obvious non-confounders. These are things like administrative data, side effects, routine labs, things that come after the treatment. And therefore, somebody who knew the setting would be able to say, yeah, these are obviously not things that you need or should control for. For each of these variables, we ask the large language model, basically, is this a confounder? We check the answer against the experts. What we want it to be able to say that all the confounders that are in the left column are confounders, and all the ones that are in the right column are not confounders. That would be success here. We have a bunch of different prompting methods. I'm not going to go super into it. These are just excerpts from the prompts. These are not the entire prompts themselves, don't worry. So the first way we do is just direct. We say, hey, here's the variable, here's the setting. Is this confounder or not? And crucially here, by the way, we are not telling it that it's from the Coronary Drug Project, but we are saying, hey, this is about, some medicine, you take it or not. We think there's some confounding. Do you think this is a confounder in this setting? So that's the direct approach. We just ask if it's a confounder. We also have an indirect approach where we first ask if that variable affects the treatment, and then second ask if it affects the outcome, which if it does both, then it should be a confounder and it should be controlled for. We have some other methods too. We provide a list of potential confounders, have it pick from the list. We have a sequential method, which has it work through this indirect thing, but like one step at a time. Lots of different things that we do here. If we just did it once and it didn't work, then that wouldn't really tell us that much. So we try a bunch of different ways. So does it check the experts? Does it match the experts? And then also, do we have consistency here? So we ask each of these prompts 10 times and we see if we get the same answer or different answers. We also try changing a couple of irrelevant details to see if that changes how the large language model responds as well. So we have a big graph here, but the basics of that is this. So for these first four rows here, original, added in 2016, expert, added, and final expert, these are things that we want to classify as confounders. And so all the blue there, that's good. The more blue in those first four rows, the better. These last two rows, trimmed and non-confounders, those are the things we want it to say are not confounders. The more blue there, bad. We don't want blue there because blue says that it's saying that something that is not a confounder is a confounder. That's a misclassification. So the large language models do a very good job at classifying the original set of confounders, right? So that original 1980 study, very famous, and if that original study said that the variable was a confounder, then the large language model also generally says that it's confounder. 90 to 98% of the variables that were flagged as confounders in that study are also flagged as confounders by the large language model. It does a great job on those. It does not a very good job at any of the follow-up studies. So those follow-up studies that revisited that confounder set and added some things and removed some things, which improved the performance of the confounding correction, right? Remember, we went from basically having an intractable problem in 1980 to a very solved problem in 2024. However, it does not actually mimic those responses, right? So we get about 30% to 50% based on model for the variables that were added in 2016. When we go to the 2024 paper, it's a bit better, but not that much. We sort of are in the 50 to 70% range also for how well it can map onto those confounders, right? So we don't get very good success for any of the follow-up papers so we are mimicking what an expert would have said in 1980. We are not mimicking what an expert would have said in 2024. And then the next part of it is we have very poor specificity here, right? So it's not just a case of how well does it point out the confounders that are confounders. We also are very concerned with the fact that it might point out confounders that are not confounders. So in those bottom two rows, the trimmed and non-confounders that we should not be classifying as confounders, it does a pretty poor job, especially for the variables that are trimmed. Almost all of those, 80, in fact, more of those than for the expert added variables, we are classifying those as confounders. It just likes to say yes, is the thing that we found. It loves to say that something is a confounder yes. And this was across models. It tends to say yes a lot. Also for the variables that are non-confounders. Now, these are pretty obviously non-confounders. Any expert, I can tell you, even someone who's not a medical expert, should be able to look at these and say, no, that's not a confounder. And so it does do better on these. But even then, we get a lot of confounder designations, about 40% for Claude 3.5 and GPT-4o. We're always classified as being confounders, even though they're definitely not. And then a further 40% were sometimes classified and sometimes not classified based on the 10 different times we asked. So not great performance there. We are not very good at specifying things that are not confounders. We also get inconsistent responses. So when we asked 10 times, only about 40% to 70% of the variables based on method gave the same response every time. The rest flipped from response to response. So whatever retrieval or potentially reasoning it was doing, it was not very consistent at that. And also, this is concerning as well. It was swayed by things that shouldn't matter. Now, this is the slide that I think is probably going to be improved the most with newer models. But basically, we changed unimportant things about the way we prompted things. So like phrasing, that direct versus indirect prompting was very inconsistent, whether a given variable would be classified as a confounder or not, simply based on how we asked the question, even though those logically have the exact same content, the two different prompts that we asked. Even more concerning is the option order. So we basically gave the large language model a multiple choice question to answer. And simply shuffling the order of the questions led to big changes in the ways that the large language models responded. You sort of want things along the sort of trace here, the sort of diagonal coming from the top left to the bottom right. That indicates consistency in the from bottom left to the top right. That's what I mean. So that indicates consistency. We certainly get some weight there, but there's also a lot of variables where you even have cases where change in the order changed about 5.8 or 16.3% of variables from being never designated as confounders to always being designated as confounders. So overall, some things work. It's very good at flagging those original classic 1980 confounders, which sort of supports the repository idea, right? The idea that we're doing recall here, because what it's mapping is the most discussed and most famous study from the list of confounder studies that we did. The downside here is that it is not matching the most up-to-date expert opinion. So it's going to give you back what is the most discussed confounders, not necessarily the accurate confounders, especially something that is based on more niche and current information. It's also not very good at rejecting non-confounders. It is very yes biased. And so we have a lot of inconsistency as well from run to run. So there's a bunch of reasons. Basically, this is not to the point where you could actually trust a large language model to designate confounders or not, right? The sensitivity is too low, especially for new and less discussed topics, and the consistency is way, way too low, at least at current models. So, do large language models act as repositories of causal knowledge? No, they do not. There's a non-trivial rate of error in this, and this is a case where you really need to get it actually correct. If you were going to do this, you would need to get an expert to verify everything anyway, at which point just have them do it from the first case. And also, this is a very highly studied case. We have reason to believe that this would actually do worse performance, especially based on what we found about it mimicking the 1980 results if we had a different application. Now, granted, maybe there's a better prompt out there. Maybe newer models work better on this. A future model, it's silly to say that a large language model can never do something at this point. I think we're all aware of that. At least at current models, these models are one generation old. We're still to redo this with the newest models. We'll see what happens. But generally, this does not structurally seem like something that's going to be very good at doing, at least for a while. Now, granted, there's other ways you could have large language models help you with causal inference. You could have the LLM draft a list that have expert vets, but again, why do it? You could just have the expert. If the expert's going to have to do it anyway, they might as well just do it. Also, in other contexts, validating is hard. This is a case where we have a ground truth. That is usually not the case. I'm a little over time, but I'll stop there. Thank you.
Thank you very much, Nick. It's a very exciting topic indeed, and you point to many different points. One thing that I wanted to start asking you is, in your practice, so I guess given the answer, probably I know what you'll say, but how do you see, while you have to think about the directed graph when you start trying to answer a causal question, how do you see the interaction between domain knowledge, your domain knowledge, human domain knowledge, LLMs, and causal discovery?
Yeah, so causal discovery is a different approach to this, where you are using the data, right? So what we're doing here with the large language models is not taking a data set and having it try to figure out in the data set what looks like it's causing something else. Causal discovery uses the data itself and tries to figure that out. And there are actually some papers out there that effectively use large language models to guide a data-based causal discovery process, right? This is about trying to build that causal graph and that domain knowledge in the first place. And I think that that's a very different task, right? Because it either requires you to reason through how the data was generated, which is inherently a causal thing, which you would not necessarily be able to observe in final data, right? And large language models are all about modeling and predicting the final data that it sees in its training database, right? So there are reasons to think that it would have a harder time with that. But then modeling with the retrieval question, it would make sense for it to be able to report back information in its training database if people are discussing what those causal links are, right? So trying to go from our domain knowledge, which is really the thing that builds that causal diagram, but it has to be domain knowledge, which, I mean, we've all done research on large language models, right? Or with it, right? We've asked it questions. It has a lot of domain knowledge in a lot of contexts, but that domain knowledge does not necessarily extend to understanding the underlying causal patterns, which is often a kind of domain knowledge that maybe is not as present in its training data.